good afternoon and good morning for me. Thank you very much for the very kind introduction. And it's it's always a great honor to talk to people that are in a slightly a different field and sort of like in the intersectional field. So I was asked to talk a little bit about works that I've been doing with the LLMs. So I should mention that this is kind of like a hobby of mine that turned into a bigger and bigger project over time. So in most of the cases in AI cross astronomy, we have been tackling the how part, meaning that if I have a question, how well I can use the AI to solve the question that I have. But in this talk, I want to tackle a slightly a different question, which is the what part, meaning that can AI come up with new ideas that can help us to find paths to do science. So let me start by showing you this paragraph. So this is a large language models generated proposal, and small abstract on what you could do as a PhD thesis. So if you are the expert in the field, so this is the field that I know quite well, you can see that the proposal itself is actually not half bad. So yeah, actually give you a very good idea on what might be a few key ideas that have not been put together, and what would be potentially a very good thesis. Meaning that if a first year PhD student came to me and say they want to work on these topics, I would not think it's a bad idea. So I will tell you how we get here. So the goal of today is to walk you through some of the things that we have done to get through this stage, and also the auxiliary science that we have done along the way. So most of the things that we'll be presenting today is, of course, not just done by myself. It's actually done by now a consortium that we call the UniverseTBD, standing for the other universe is to be decided. There is also sort of the sentiment that we share, meaning that in the likes of all these large language models, how should we think about science in the future? So who are we? So the UniverseTBD started with just a very small group as a hobby, but it quickly grew into a pretty large consortium, about 30 to 40 people. So we are groups of people like astronomers, software engineer, and computer scientists. So quite a lot of them are from where I am now at ANU, and including the faculty both in the computer science, but also the faculty in astronomy. I am half-half, and also the students and postdoc in the school. And also since the beginning, we kind of know that since we are tackling large language models, we do not just want to use the model. So we want to train our model, so we have a control end to end. So since the beginning, we have been collaborating with some of the experts in the domain, so including the people from Meta, also the people from UC in Illinois, to work on training a large language models. And also since the beginning, we know that whatever that we do is important to connect to the community. So we want to make sure that whatever we do can be used by the community. So this is why since the beginning, we have been working with the ADS. So the ADS stands for Astrophysical Data System, which is also the main database that we use as a astronomer. And since we have done a little bit, so this thing has grown quite quickly. It's because I started about 6 months ago, and since we started to produce some results, we are quite honored to get the support from the Microsoft research as well as the OpenAI, and there are also more and more people collaborating with us externally. So we started to work with people from the Hugging Face to have an interface to help to be used by the community. Also, recently we have been starting to talk to the national labs, both in Oak Ridge and also in Argonne. So I will tell you where all this stuff fits in. And And lots of things are also not done just in Australia, it's quite around the world. So we have been working with people in Europe and also in China and in the US, of course. And of course, we don't discriminate. We love rich people. So we also have the partner from the industry. So like some of them are ex-astronomer. So Kevin Stravinsky here led what we call the Galaxy Zoo project before, but now he's in the industry and he's also quite less supportive of the project. So we also should mention that we are in the process of thinking to make the consortium become a non-profit. So if you have like any interest and want to support us, do let me know. So of course, I know that it's a mixed bag of audience. So not all people have worked in large language models. So I thought I want to first give you a very quick overview of large language models, and understanding that will help you to understand what we have been doing. Let's start by talking about computer science, right? So in many cases in AI cross science, AI quite often take the secondary role, meaning that we treat AI as a tool to solve the problem that we want to solve. But it's also important to remind ourselves that computer science is a science, because since the inception of computer science, one of the key goals is to understand what is knowledge, right? So if you go to the seminal paper from Alan Turing, the very inception of computer science is try to understand the human knowledge. And because of that, since the beginning, being able to chat with the machine has been a big part. And things has moved like very quickly in the last few years, like if you compare to where we were, right? So chatbot is not new. So there is a famous chatbot called the ELIZA in the 1966. I believe it's from MIT, but I'm not sure. And I like the way that I describe like ELIZA is like my parents, my Asian parents, they are quite passive aggressive. So if you like ask question, then it will start to attack you, right? And of course, this has changed drastically in the last few years. If you ask the same like question to GPT-4, like GPT-4 will give you a warm hug that I always wanted. So the question is how do we get here, right? So from ELIZA to GPT-4. So if you have not been working in large language models, you might have the feeling that this come out from nowhere. And this is not half wrong, because quite a lot of things that we have been thinking in terms of natural language processing is happening in the last 5 or 6 years. So what has really changed? What leads us from ELIZA to GPT-4? There are like at least 3 main breakthrough that leads to where we are at today. So the first breakthrough come from this paper. It's called "The Attention is All You Need." It came out around the end of December, like around 2017, and then 2018. And this is truly a seminal paper. If you have no idea what I mean by that, this paper, like despite not only came out about 6 years, it has been cited 100,000 times. If you do the calculation, it means that this paper has been cited about 60 times per day. And so what is this attention thing, right? So the attention mechanism is to realize that you have a special architecture in the neural network that is doing pretty well in languages. And this is one thing that I want to keep emphasizing, because a lot of people treat neural network as a black box. A little bit of that, but not fully, right? So like any neural network that we use have what we call the inductive biases, meaning that what sort of assumption that we believe the data have. And what the attention mechanism here is to realize that for most of the languages that we have, the information is sparse and it's long range, meaning that if I show you a sentence, I do not need to focus on all the words. I only need to pick up like a few words, and that will give me sort of the understanding of the sentence. And this type of long range and sparsity in languages is actually quite prevalent. So it does not matter if you speak English or if you speak like High Valerian, it will be the same, right? So it's always a long range and sparse. And the models that we use the attention mechanism is called a transformer. And this has transformed the field. And a side note, so like even though like this is not like about AI being applied to astronomy, but this type of like models, of course, has also been applied massively into astronomy. So like including my work from my students and postdoc, we have been like applying the transformer models to time series as well as spectra, because both spectra and also time series have long range and sparse information. So why this is so important? So the first revelation that finding the right architecture for languages is absolutely critical. And this is shown in this quite amazing plot in the paper from OpenAI that are described like GPT-4. So what you are seeing here is the y-axis here is the performance of the models. I think like this is the perplexity. So how about you can predict the next tokens as a function of the size of the models. And the white dots here are showing you some of the experiment they have done. The impressive part is not the white dot, it's the dashed line. So the dashed line here is not a interpolation, it's a forecast of the performance of the models, meaning that like before OpenAI runs the models, they can like already exactly like predict how good the models would be in terms of the perplexity. And this all leads to like if you find somewhat a right architecture, then you can keep building bigger and bigger models, and you will still keep improving. And this is also why like people like believe that, not believe, but this is why like people are investing massively into large language models, not because just a hype, but rather like at this point we have seen no plateauing on the performance. Yes, it's getting more difficult to improve, but you see like all this improvement can be extrapolated. And because of that, this leads to the second revelation in AI, which is not only attention is all you need, is money is all you need, right? Because you can keep building bigger and bigger like models. I believe this is to size in terms of the parameters, the numbers of parameters. So you go from a Mars-sized planet from GPT-1 to Earth-size to Jupiter, and who knows what is like GPT-4, right? Because like it's unknown. And because of this right architecture that has been raised to make bigger and bigger models, so we know that the bigger models is better. So this is called the Moore's law of the LLM, meaning that the models has increased by about a factor of 10 per year. And this is also like jokingly called the Huang's law, which is the CEO of NVIDIA. So this is the second revelation. The third revelation is that like, at some point people kind of like believe we can do everything with self-supervision and unsupervised learning. But people also soon like realize that languages itself or logic itself is a very complex matters. So it does not just help to predict the next token. Sometimes you need to define what you really want. And this leads to sort of the third revelation that if you have a big model, you still need to instruct the models and align the models in a way that you want it to perform. And this is called the RLHF, the reinforcement learning from the human feedback. So this is a very quick overview of what happened in the last 6 years. The question is, why are we here, right? So why do you need a consortium to do the LLMs for astronomy? It seems like OpenAI is doing like very well, and Meta and Google are doing like very well. Can you even compete with that? The question of that is unknown, but it's also known that like at least in the earlier version of the large language models, the general models are not doing that well in a very specialized task, right? So a good example is BART. So after the GPT-4 is released, or 3.5, then Google released the bots models. And in the first version of the bots illustration, the human asked the bots what type of a discovery I can tell my 9-year-olds about James Webb. And the bots reply, well, the James Webb took or will take the very first picture of planets outside the solar system. For non-experts, this seems perfectly reasonable because James Webb do have very good imaging capability, but also one of the main signs for James Webb is to understand the exoplanets. But if you are expert in astronomy, then you know that this statement is completely wrong. The problem is that we have taken the first picture in 20 years ago with what we call the adaptive optics. And this type of like very specialized topics used to be quite struggled by very general models. And this, of course, have real life consequences, right? So like Google lost like 100 billions in a week by showing the wrong example. So this leads to why we want to do like what we want to do in the universal TBD. So we want to have a specialized trained LLMs for astronomy, beyond just the GPT and all these public models out there. So if you have like follow what I have mentioned in the first part, then you know that in order to train have the LLMs for astronomy, you need two things, right? One is to train a big model, the bigger the better. Also, like after you train the model, you need to learn how to instruct the models and align the models to do what you want to do. And this is also the two parts that we have been doing. So the first part is to train models. So we started by curating the archive paper from astronomy. Like trust me, like this is really tough because the people in the 2000, they do not know how to write a proper latex. So it took us like a long time to clean out the latex. But once you have curated them, then you can try to fine tune models based on just the astronomy paper. And this is something that we started as a fun project. So we started with the pre-trained models from Meta called the Llama, and then we fine-tuned that on the abstracts on the astronomy paper. So this is a pretty small project. Like you can do that in a few days of GPU, led by a student. So this is published in September. This is also the first and also the only specialized model in astronomy. So the first part, we take the archive, the abstract, and train the small-ish models, 7 billion models. And because it's just trained on the abstract, so the goal here is to get a better semantic representation of astronomy and also doing some text completion of the astronomy. I will show you some example later. And this, of course, the fun project that get quite a lot of attention, and then we have been building upon that and grow more and more. So the second version that we just released literally, I think today is Wednesday. I think this is officially published, I think like Friday or Monday. So we also further release a second model. It's called the AstroLLaMa Chat. So this is the first two models and still the only model in astronomy. So what we are doing here is expanding beyond the abstract with the introduction and the conclusion. Also, we know that for a small-ish models, if you train that with a specialized data set, it tends to forget what it knows, right? So even though the Llama 2 do know how to do Q&A, but if you look at the AstroLLaMa, it's not doing that well with question and answering. So we ended up curate a bunch of astronomy Q&A and then put that back in to enhance the chat and QA capability. So what can it do, right? So it's actually a very importantly, I should mention that both of these paper are led by the PhD students, right? So the goal here is to say, we want the student to really lead this project, because some of them either do not have the background in astronomy or do not have the background in computer science, but we want to make sure that we give the training for this student to do the intersectional science. So what can it do? So the first one is text completion. To understand that why we need to train a specialized models, you need to see like a few tasks to see in what like cases it works better than a GPT models. One of them is completing the abstract for the first version. But this is no surprise, because this is trained on the abstracts. So for example, if you take a astronomy paper, you started with the first half of the first 1/3 of the abstracts and let it to complete. So in this paper, it's a real paper. And here we are looking at the Magellanic Stream. So the star that should be there due to the interaction of the large Magellanic Cloud and the Milky Way. And this paper is focusing on finding those stars. So if you ask, say, ChatGPT, like even with a GPT-4 to complete, one of the characteristics of that is that the GPT will tend to hold back. So you give you very generic responses, basically like Neil deGrasse Tyson. You just say, well, you know, there are stars are amazing, black holes are amazing, like, you know, like we love them. But first of all, it's unclear if GPT like do not know the details. Most likely it knows, but because of the alignment that is subjected to training the GPT-4, it tends to hold back quite a bit, meaning that if you do a very generic prompt, it will not do that too well. But if you ask the same thing for AstroLLaMa, the actually works pretty well, right? So in the AstroLLaMa one, we actually try a few examples. In most of the cases, it does give you very specific completion, meaning that, you know, if you look at the Magellanic Stream, it will say, well, first you need to do some wide field imaging. So it kind of like pretend that it has done the project, say that, you know, we look at the wide field imaging, and then we confirm that with the motion of the star, with the Gaia satellite, and then we pre-select things with the metallicity of the star, and then we follow up with the spectroscopic data. And then it starts to make up some numbers, which is funny because like this is part of that we do not constrain AstroLLaMa. So, you know, it's glass half full, half empty, because in GPT-4, it tends to hold back, and there's no way to reverse engineer that, right? Because it's not like open source. So one of the advantages that even from here, you can see that for very specialized tasks, AstroLLaMa do understand like astronomy better. And also you can really tailor the way that you want it to be. So nice. And so where are we going? So like any models that we publish is always like few months like behind from what we have, right? So like internally, we do realize that the 7 billion models in most of the tasks is not like doing as well as GPT-4, right? So like Q&A is not like at least you ask very specialized astronomy like problems, it tend to not outperform the GPT-4. But of course, this is a very small model, so this is like at least 10 times, like if not 100 times or more smaller than the GPT-4. So we are scaling up to what we call the AstroLLaMa Big. This is also done in training. It's not released yet, so because we are still beta testing. And this is really like getting quite expensive. So each time it's like the compute is increased by a order of magnitude from 10 GPU to 100 GPU days. But this is still affordable in the academic setting. But of course, this is affordable because we are doing what we call the delta tuning, meaning that we are only fine-tuning a small part of the neuron in the transformer. We are not letting all the neuron to update. For expert, we are using like a bunch of like LoRa and flash attention to keep it down to 100 days. Of course, we're expanding this because what we have shown that, like, at least for some of the specialized tasks, this type of like approach, small-ish like models, is very funny because we call a 10 billion parameter like model small. Can works pretty well, right? It can outcompete in some of the cases with a GPT-4. So we get some attention from people in the national labs, and we might be working with them to really scale this up to what we call the continual pre-training, meaning that we are training on all the parameters and letting all the parameters to update. And depends on how you do that. This will cost about typically 10 power 3 GPU days to about 1 million GPU days. But this is still like doable in the national lab. So this is what we are doing next. Okay, so that's all the baseline. So what we want to do, right? So once you have such a models, what is the goal here? In the UniverseTBD, we love to think about the past, the present, and the future. So we want to change the past, change the present, also change the future. So who say we cannot change the past? Let's talk about how we change the past. So one thing that we kind of like notice more and more, especially in astronomy, but also the other field, is that how we assign credit is broken. This is actually well illustrated by this plot, which I love quite a lot. So the individual data point here show you a different subfield in science. And the x-axis here show you the numbers of papers in the subfield. And the y-axis here show you the Gini factors of the citation, meaning that, do the cited paper get more cited over time? And you can see a very strong correlation. And this is not too surprising. So intuitively, what this is saying is that as the field become bigger, no one reads papers. They just cite whatever the people cite, right? So this will increase the Gini factors, meaning that sometimes a very good paper never get cited because you just fall into the wrong side of the coins. And this become more and more problems as the field keep getting bigger, right? So, and this is of course very universal. So these are different lines here, I believe, are different fields, right? Like physical sciences or biology, they all have the same problems. So how do you change the past? So one way to do that is to be able to read all the papers and then just assign the credit based on what the paper is written, but not based on how much the paper have been cited. The problem here, of course, is that no one can read all papers, but a machine can, right? So the goal here is to say, well, for every papers, can I actually extract an embedding from the papers that truly represent the knowledge in the papers? Of course, for any large language models or any AI, you can always extract such a embedding, but the question is how good the embedding is. And this is also a task that we find specialized models are doing better. So how do we show that it's doing better? So one way that we do that is to look at the cosine similarity between two papers, meaning that for individual papers, I'm looking at a vectors, I'm looking at the angles between the two papers. So if they are large, meaning that they are close. If they are small, meaning that they are not similar. So here I'm showing you all the cosine similarity of all 300,000 papers in astronomy judged by GPT and also AstroLLaMa. So the yellow bar here show you the cosine similarity of any two papers in astronomy. You can see that in the GPT-3, you will think all the astronomy papers are just astronomy papers, right? So in the outsider, all astronomy papers are about stars and galaxy and planets and black hole, and they are all quite the same. Of course, this is not true, meaning that the GPT do lack the nuance understanding of the topics. The science distribution here show you the cosine similarity from AstroLLaMa. It goes from really small to very large. meaning that the AstroLLaMa, do you believe even these are two astronomy papers, some are really more similar than the other? To show you more specific examples, so there are examples that the AstroLLaMa disagree with the GPT-3, right? So these are the two papers that the GPT-3 thinks they are quite similar. They are 0.79 in terms of the cosine similarity, meaning that GPT thinks these two papers are similar. But if you are expert in the field, then you know that this is completely bonker because these two are two different subfields. And the reason that the GPT-3 thing is very high, I believe, is because both of these cases, they have the words magnetized. So even one in like American spelling, the other in Australian spelling, is still I believe these two papers are the same, right? So like GPT without the nuance knowledge do fixate on some of the keywords. But the AstroLLaMa actually gave a very correct understanding that these two papers are not the same. You can do the other way. So these two papers are more nuanced. So one is using the Spitzer infrared satellite to look at a nebula, and the other is looking at the H2 region, the ionized hydrogen regions. So for GPT-3, it would not know what is happening. Like this seems like two papers that might be similar, but all astronomy are the same, right? But AstroLLaMa actually understand that these two papers are quite similar. So these two papers, like despite they are looking at different signs, they are looking they're looking at different phenomenon, but they are all looking at the same signs of star formation. So this shows you that even the very simple model that we trained with one day, the AstroLLaMa 1, just with the abstract, you actually understand how to get the embedding much better than the general models. What can you do with that? There are lots of fun projects that we are doing in UTBD. One is called Pathfinder. So we are just having some applet that will help you to find the correct paper to cite. So you can put in any paragraph and you can find the correct paper. We will summarize the paper for you. So this is not completely avant-garde, because I know there are also people doing that. We also looking at the landscape of the research. So we get the embedding, we run a UMap, we push that into Midjourney to make a beautiful plot. We call the landscape of a cosmology paper. So you get all the mountains and the valleys. But you can also look at the evolution, right, of the field. And this is quite insightful. These are very simple. So people in Google have done that called n-grams before with just the keywords. But here you have a better embedding. So you can look at the evolution, say, certain concepts like cosmology, dark energy. This is quite interesting because in the 1990s, the cosmology is quite hot because there's no data, so the theorists can say whatever they say. So there are lots of theoretical work being done. Of course, they run out of things to say after you have no data, so it dies until the first survey, the Sloan Digital Sky survey launched. So you get a jump in terms of the research, and then slightly slow down in the last 20 years. James Webb is the obvious one. So this is the James Webb Space Telescope. After it got launched, it just shoot up, right? There are also things that are quite interesting that I myself did not know. So most people believe that things that the machine are learning in astronomy is quite new in the last 5 years, but it actually no, right? If you look at the papers, even in the 1990s, there are lots of people talking about a neural network and apply that to astronomy, but it just get forgotten. But if you have a machine that can read all the papers, then you can start to recover some of this evolution of the field. Okay? It will also help you to understand how to allocate the budgets. So this is fun. So hopefully the stock market in astronomy will goes up. The also thing that we are doing, so in astronomy, we have a very prestigious review called the Annual Review of Astronomy and Astrophysics. It's called the Annual Review for a good reasons, because if you have a question, then you need to wait for 1 year or more, like before the review comes out. So we are doing like a lot of things. So we have a project called AstroBytes, because that is a very famous a student-run a website called AstroBytes. So we have an AstroBytes that is digesting the paper with machines and try to summarize that for you. So that is how we change the past to assign the credit, how we change the present to speed up the research. But that's not what we're here for, right? So the topics I want to talk about is to forecast the future, to understand, can a machine come up with good ideas? This is come back to the question that I mentioned in the beginning. So a lot of things when we think about AI cross science, AI is taking the secondary role. It plays as a tools to solve the question. But I think we can go beyond that. If you want to have a AI scientist end to end, then you want to make sure that not only it can solve the hows, but it will solve the what's. And this is what we try to do. But that is, of course, more tricky because, like if you remember the beginning, we mentioned that pre-training models is just one part. But you want to instruct the models to do exactly what you want to do. So in the UniverseTBD, we have the program called Hypogen, stand for hypothesis generation. And this is how to solve the whole landscape that how we are doing this. So of course, first of all, you want to make sure that your hypothesis is robust, meaning that you want to make sure that you have a high fidelity, meaning that you do not want to just ask the machine to hallucinate. And this is not too hard to solve because the thing that I mentioned earlier, you can use this as extracting the embedding into a vector, a database will largely solve the hallucination, because now for any sentences that you say, you can check against the vector database to see if this is factually correct. But just making sure that what you say is factual, that does not make your idea fluid, right? So the second part that we try to tackle is making sure that like any ideas that we come up with is very fluid, meaning that it flows well. And we have tried different ideas, but one thing that we find very useful is adversarial prompting, meaning that not only you have one LLMs, but you have two LLMs that talk to each other. So this comes back to the first slide where I show you one of these small snippets of the hypothesis. This is actually not the first proposal from machine. Actually, it went through a few iterations. So first time it proposed something, the other models will criticize. So it serves as a referee or your supervisor to criticize what is bad with your ideas. Because it has the access to the database, so each time it criticizes you, it also gives you the references, the correct references of why the idea is bad. And based on this criticize, it become the context that we put into the LLMs, and the LLMs will come up with a revision. So if we went through a few revision, at least to solve the things that you see. So the adversarial prompting is like giving you a supervisor or a referee to help you to improve on your ideas. And this actually works, right? So how we show this works is grade the hypothesis with humans. So the y-axis here show you the grading from 0 to 5 by humans. The axis here is sort of the knowledge database the machine have. On the left-hand side, the dark green here show you the case without the adversarial prompting. This is kind of like a grad student without a supervisor, right? So if you have a grad student that without a supervisor, you can read as many papers as you want, but the proposal that you come up with does not improve. On the right-hand side, the light green here show you the case where you have your supervisor or a referee, right? So in this case, the more paper that you have access to will give you a way to synthesize a more interesting ideas based on the knowledge database. And you can see that we are like limited by a small number of papers here, because when this work is done, so the like many things I present today is work in parallel, so by a different subgroup and students, and this is done by a GPT-4. So we are not using like AstroLLaMa, because this get quite expensive quite quickly. So even though we are like, supported by like Microsoft and OpenAI, and this is part of the reason why we need a lightweight, small scale like models. Yes, like we know that this can be done with a GPT-4, but this can get quite expensive quite quickly. This is the second part, like ensuring the fidelity, and also this is not the end of the story, right? Because just being able to say something very fluid, it does not mean that you are very creative. So the third part that we have been like actively like tackling, which is come back to the Turing like question, like how the machine thinks, how the human thinks. So how do we mimic an environment where the machine can mimic the human? So the approach that we are taking now that seems to be quite successful is by mimicking kind of a workshop scenario. So what we try to do here is to have a generator. The generator is like having short conversation in the workshop. So we ask the machine to generate, I think here, 3,000 short ideas, based on the papers. Like we call flip bips, meaning that you have a short ideas like three sentences, but also, a critics of the ideas. And it's also in 3 sentences. And then you collect all these like 3,000 ideas, and then you go home, and then you will grade your ideas, right? You have many conversation with people in the workshop. You go home and then you write it down, and then you grade all these ideas. And this grading is also done by the language models. So you genetically evolve the ideas over time. And we believe this is also how the creativities come about. And this is why you go to workshop, right? You have short like conversation and try to like evolve the idea. And this is really quite something that is quite new. So this is absolutely preliminary, but we actually have a competition. So we have blind tests of 2 hypotheses. One is from the hypogean, like doing all these 3 parts. We have the real proposal by human. We have some few shot and a 0 shot from a GPT. This is still very preliminary, but basically the hypogean have a elo of infinite, because it always wins. So the ideas that you come up with after sifting through a lot of small ideas do tend to be very robust. But this is again super expensive. Like this is done by GPT-4 with all these things. This paper is I think it costs like 7,000 US a dollar. And this also leads to the reason that why we are building our own specialized models, because this get too expensive. Like if you just do that with a GPT. So I should also mention that this is very small part of what the consortium has been doing. So if I like want even more crazy like ideas, I have some extra slides. Truly, like at this point, if you have been training large language models and thinking innovatively how you interact with that, like really the sky is the limit. And for younger people in the house, this movie is called the Jurassic Park, right? Yeah, but shall we do it, right? So like, can we do it? I think yes. Shall we do it? I'm pretty sure I will be asked this question a lot, so I decided to give you my take like before you ask me. So first of all, like, can we have an end-to-end like AI scientist? I hope to convince you that not only AI can help you to do science, it can come up with the science by itself, and then you can do like end-to-end. Should such a AI scientist be ethical, right? That's a question I get asked like a lot. The closest like analog that I can use is chess, right? So I play chess and I still watch chess. I remember a time when I was young, Deep Blue first beats Kasparov, and all people think chess is over, like no one will play chess, like because like AI is better than us. But it turned out to be wrong, right? So if you look at chess, I think chess is much more like exciting now. than 20 years ago. That reason is because when AI outcompete human, like the human will still play the games, right? So I feel like doing academic is a pretty fun games that we want to play. It does not like matter if the AI beats you. In fact, it's better because I grew up in Malaysia where science is not too abundant. Used to be, you need to grow up in Soviet Union to become the chess champion, but no longer, right? So quite often you see in some very exciting chess player from country from nowhere because you can play with the AI. And I do think that we are really quickly entering this era that you do not need to be, at Harvard or MIT to do the best science, because the AI itself will contain as much knowledge as some of the most prominent figure in the field. If you take this view, then the only question that you want to ask is why astronomy, right? Why do you choose astronomy to study this type of inquiry? Few reasons. One is no one dies. This is particularly important for coming up with new ideas. There are a different field where this becomes highly unethical, right? So if you ask a machine to come up with a drug or something, people do that, but it comes with quite a lot of ethical implication. But if you want to have a sandbox to understand how the knowledge get generated, the astronomy is the best place to do that. And also I started to be approached by lots of people in different subfield like geophysics and so forth. And I'm really quite amazed at how badly curated the literature are in some of these subfield, like compared to astronomy. So astronomy has always been having a very well curated literature, and also we have a lots of. So the things that I did not show is you can go beyond just doing the literature. You can use the LLMs to call the API to solve the science. And a lot of the code is open source, the data is open source, and the literature is well curated in astronomy. Also importantly, it has a very long history compared to many physical subfield in physics, right? So if you look at nuclear physics or atomic physics, most of the subfield in physics have a lifetime of 20 to 30 years. But astronomy has been here for a long time. Even you look at the modern day astronomy, it has survived more than 60 to 80 years, right? Meaning that we have a large a literature. If you want to show that we can auto-regressively generate knowledge, we have a long baseline to test the ideas. So that's me in the future, and thank you. I'll take question.
Okay, so as usual, what we'll do is we'll take questions from people in the room first. Anybody online, please just drop a question in the chat and I'll read it out, or otherwise put your hand up and I'll enable you to unmute yourself and ask the question. Okay, so we'll start from people in the room. Has anybody got a question in person? No, if not, I've got about 10. So I'll sort of start off with one. So some kind of problems with large language models are, yes, you need to have a good model, you need to have powerful GPUs, but you also need to have enough training data. So if I've understood you right, you're already at the limits of the training data as you can kind of get it from astronomy. I mean, if you're taking all the astronomy papers on the archive, everything on ADS, there's not more papers for you to kind of get out there. So I was wondering, what are the limitations of that? And is there any sort of, I mean, you don't really want to reintroduce your own biases as to what papers you should more write than others, but is there any thought done into the processing of the papers or the weighting of the papers?
Yeah, it's no. So the reason is a conscious choice, just because we try not to. The thing that the worst that you could do is to do the citation, right? So this is why we try not to do that, because we want to go get around the citation. It's unclear how do you select a good paper. I think there might be a way to do that. So the path finder, we also start to try to understand how do we objectively define a paper is novels. it's possible, you can think about the embedding space and see if a paper at that time is truly producing a embedding that no one has mentioned before. But at this point, we know, so we try not to do that. But you also write about the number of tokens. So this gets a bit technical. So the astronomy archive have about 5 to 10 billion tokens in total. So if you just collect all the papers and tokenize that, that will be around 10 billion tokens. And if you ask what you can train with a 10 billion tokens, the sort of the consensus in the industry is you can do a continual pre-training, meaning that you still need to start with some pre-trained models like Llama. You cannot just train from scratch, because training from scratch will take about hundreds a billion tokens. So if you take the number of tokens, then most likely the best you could do and find that still useful is the continual pre-training, meaning that you update all the parameters, but with a pre-trained models. And this is sort of the steps that we are doing next. So we have delta tuning the 70B models, and we are now hoping to do a continual pre-training with the 70B models, and that will cost about 1,000 GPU days, which is about $4, $24 per day times 1,000. Then you need about then you need about 30,000 per training. It's possible. So for big super cluster, this is completely doable. So after that is unclear. So unclear is a strong statement, because the thing that I did not mention is to do this thing with different subfield. So we try not to do all subfield at once. So we want to get away with the general models and try to have small-ish specialized models. And this is called the mixture of experts. So there are lots of people in the industry are doing that. So the training small-ish specialized and ask them to coordinate. So that's sort of the direction that we are going after we have do the continual pre-training.
Okay, thank you. Are there any other fields which have kind of nicely curated papers like astronomy that are kind of promising to go into next?
No, yeah, I look at geophysics is not that straightforward. That is quite crazy.
That's a shame, because you can imagine that the boundaries of the different fields, in astronomy, might look like a chemistry paper, might look like atmospheric science paper. So
yeah, some is better than the other, right? But sort of like biological sciences are better just because they have money. I think that's one of the main things. Physical sciences is good and bad in the sense that what we are doing here, we are still the only group are doing that, right? To our best knowledge in astronomy. But in biology, there are lots of groups are doing the same thing. The physical sciences is good in the sense that the competition is low, and you can learn and play with your own pace. The bad thing is that the data are less curated, and all these are more tricky.
Mm-hmm. Okay, I think finally from me, people don't tend to write papers on their failures. So is there any limitation to your kind of training data because of that? People emphasize their successes, they exaggerate, they don't say I tried this, it failed. Don't go down this road.
Yeah, so this is beyond what I presented today, but that is a project we are working with Microsoft, and quite beyond what we show today. But you're right that one of the things that we realize is in terms of coming up with solver, right, the plan, GPT is very bad at being critical. So it is quite good at critical in terms of ideas, because somehow we love to attack people on papers, right? But you're right that we never say, well, I do this experiment and I fail. And this is why when we ask them to solve a question, right? I think this is like also a way, like a problem, not problems, but I think the easiest thing to think about is like mathematics. If you want to have a very good theorem prover like LLMs, then you want to make sure that you know how to be critical of your logics. But in most of the paper, it's just like, this is the proof. I come out from nowhere. I am a genius, and this is the proof. Right? You never have written down all your thought process, and this become a problem. Like at least for this particular project, where the models are not being able to critical of its own steps in solving, say, a math equation. Yeah. But still, pretty critical of like people ideas. If you give a broad strokes of like what are the proposal, it gives you a very good referee. But just very special. When you get down to specific solver, that is not very good at being too critical.
Okay. Last chance questions for anybody. Okay, if not, we'll thank our speaker one last time for, again, joining us crazy early in the morning. So thank you.
I'm going to make it. Bye-bye.
Okay, so we'll be back next month with Parisa Rashidi from the University of Florida, who'll be talking about the use of AI in improving healthcare, in particular, operations of intensive care units, which should be really interesting as well. So hopefully see you all there next month. Okay. Thanks very much, Yuan-Sen.